Okay, continuing with 6.4. And day one, we talked about exponential growth. So here's a little bit of review for you for exponential growth. And then exponential decay is basically the opposite of exponential growth. Your equation still needs to be in the form of y equals a times b to the x power. So it still looks like this, but if b is less than 1, it has to be more than 0 as well, then that's an example of exponential decay. If you graph exponential decay, like we talked about previously, the basic shape of the graph, if this is my x-axis and this is my y-axis, then the graph would go down from left to right. It would look like this. It would actually keep getting closer and closer to 0 or the x-axis, but never touch it or never go through the x-axis. And then kind of like with exponential growth, I'm going to break this equation up even further. The opposite of exponential growth. So your equation would look like this. Y is equal to A, which is still the initial or starting amount, times a quantity. Instead of 1 plus R, since exponential decay is the opposite of exponential growth, it's actually 1 minus R, still raised to the t power. So all the different parts of that equation or function are basically the same, except kind of the opposite. A is still the initial amount. R, instead of being the percent increase, it's the percent decrease. And then you would change that from a percent to a decimal. So percent decrease, again, as a decimal or in decimal form. You could also refer to R as the rate of decay instead of the rate of growth. And then T is still the time. And then kind of like with the 1 plus R, that's the growth factor. The 1 minus R is the decay factor. And then we'll use that equation and apply it to specific examples of exponential decay.